Let's do a couple more examples of using Kruskal's algorithm to find maximum spanning trees. So let's return to the second graph from the packet that we've already found the minimum spanning tree for, and let's instead find the maximum spanning tree and the total cost. So we're going to start with the most expensive edge, because again, that's our adjustment if we're trying to find maximum spanning trees. 65 is the most expensive. Then 42, the meaning of life. Then 39, I believe. The only thing you need to be careful about is that you are going in order. If you go out of order, you could mess up and you could select the wrong edges. So just be careful. I usually am probably not as careful as I should be, but nonetheless, 36 would be the next cheapest edge. 35 is the next, but again, that would be a skip because that would form a circuit between B, C, and F. Next cheapest would be 34. Next cheapest is 33. Then comes 30. Then 25, which would create a circuit between H, B, F, and G. 24 would also create a circuit, no go. 23 would create a circuit. And again, we're going to keep going until everything's connected. So next up is 22, which would bring A in. And you probably could have used some common sense to say, okay, well, all of these are all connected. The only one left is A, and I'm going to need the most expensive way to do that. So you can take some shortcuts, but I'm trying to follow the algorithm very closely. Keep going. Use the biggest numbers in order and skip when you have a circuit. Continue so doing until you have selected n minus 1 edges, and this would be our max spanning tree. And you can calculate the cost obviously yourself if you so desire. Let's do one more example, as well as a group activity. And basically, I'll leave the group activity for you to practice on your own. Same with these. Feel free to pause the video and try them on your own before. And if you want to check your solution, or if you're getting stuck, then you can just watch me solve them as usual. But let's solve number one on the third page of the packet. It says the potential daily revenue for building a trolley network between the following parts of town is given on the following graph, where the numbers are in thousands. Find the most profitable minimally connected network. Or AKA find a maximum spanning tree. So here, it looks like we have 6 parts of town, A, B, C, D, E, and F. And our goal is to construct trolley lines in between these parts of town. So we can imagine currently there are no trolley lines. We don't want to build every single one of these trolley lines. That would be horribly impractical, right? So we want to know which are the trolley lines that are the right ones. Which parts of town should we connect directly together? And a lot of times in a real city network, there's a lot of things to be considered other than just straight profit or revenue, because what's often more important is efficiency, making sure people can get to work on time. But there's a lot of factors. So cost is or revenue is not the only factor. But let's assume that our company is selfish and we just care only about money. Or the revenue that we're getting. Sometimes that would be a valid concern, and sometimes we'd want to take other things into account. But basically, we're gonna be finding a maximum spanning tree because we want to build the most expensive edges only here. So applying Kruskal's algorithm, we're gonna start with the most expensive edge. Sorry, ooh, my tablet is freaking out. I think I'm back in it. Whoops. Technical difficulties, give me a second. I had to reload the website on my tablet because I am trying to make it larger, but it decided to do something that I didn't want to do. Okay, so basically starting with the most expensive edge, which is 62. And sometimes, and this is something I mentioned in previous chapters, sometimes the graphs aren't made very well where the numbers are kind of hard to tell where they're at. But here, if 41 is this one, I believe 62 has to be this edge because it appears as though 42 is this one and 30 is this one. So sometimes via process of elimination, you can kind of figure out, well, which edge is which. But I'm going to try very hard to make sure on exams you can tell which is which. But this is something where you could always ask me, or when you're drawing your graphs on paper, if you're ever having questions, you could mark that. But since we're doing our exams online, it should be pretty clear, hopefully. And I'll try to avoid choosing questions that are hard to see, but I can't always control it, myself. When I'm actually giving you a physical exam and printing it, then, I can make sure it doesn't look like this. But anyways, 62 appears to be that edge. 60 is the next most expensive edge, which appears to be the connection AE. Then next up would be 48, which I believe would be the edge FD. And notice that when you're going, the one thing you can't do is circuits. So this would be a step where it might be a cause for concern because it sort of looks like there's a circuit here. But since there are no vertices here, what that's implying is that this is not a stop. This would not actually be a circuit. Because really, if I'm imagining these tri-lines, I've connected AE and EC. So if I was in any of those places, I could get from one to the other. But FD is built on a completely separate line. So I'm a little tired, and sometimes I slur a little bit when I get a bit tired. But this is a completely separate line, and there is no overlap or intersection between those trolley lines because there is no vertex there. So that's totally fine. That's my point. Next cheapest edge would be 43. Again, this might be one where it might seem like, okay, is this a circuit or not? Because it kind of looks like it. And that's exactly why I wanted to do this example. This is a slightly harder example when there are so many more edges. The more edges, the harder this is going to get. But also, there are no circuits here either, because notice that kind of unites the trolley line AEC to FD. Those were currently not intersecting at all. Now FE is joining them together. Now I can get between any one of the points. And again, this is not a circuit. This is not a circuit. This is not a circuit. So because there are no vertices at these intersecting points, there are no circuits there. We're still fine. Next cheapest would be 42, which I believe is the edge between BD. And actually, I didn't even need to skip anything here because none of those actually form circuits. Now, it's possible that there were circuits in this problem, but it just so happened that we didn't have to skip anything, and we found our max spanning tree as such. And notice, again, the way I can be more certain is all of the vertices are now built into this trolley network, and we use 5 edges, the minimal amount. So I can be feel pretty safe that I didn't mess up, that I didn't use any edges I was not supposed to. And then I could find the daily revenue here, which is usually the total thing we're looking for. And adding all that up would be 255, and this was in thousands of dollars. So, our trolley line, whether this number is realistic or not, will be making $255,000 per day if we do this construction. And obviously, if I was to use other trolley lines, we'd be making less money, and we would have less obviously our goal here was to maximize our revenue. But again, returning to hypothetical problems with the minimum spanning tree, this is not necessarily taking account efficiency of travel. Like, let's say, for example, I live in city B or part of town B, and I'm trying to commute to C because I work there or whatever. And I need to use a trolley lines because I don't have a car or whatever. Notice that obviously the easiest way for me to get to B to C was to go here, but in this configuration, we did not use B to C, so this would not be a valid trolley option. I would have to use the actual trolley lines within the network, which would be the ones that we selected in our MST. So I would have to go B to D, D to F, F to E, E to C, and the degree of separation between B and C in this solution is actually 4, which is quite a lot. That's a lot of trolley lines to get from B to C where they appear to be very close in the actual network. So again, this is a problem with spanning trees. As I said before, sometimes those solutions are not really efficient for the sake of the actual traveler. But for the actual configuration, it does matter. Now, if we apply all of this theory to, say, internet networks, a lot of times it depends on the speed of travel between these things, and certain things travel by the speed of light or the speed of sound or whatever. Certain connections are faster than others. If it's a trolley, it might take us a long time, but if this was, say, electricity, it's not necessarily a concern with how long does it take. Degree of separation may not be an issue. It just really depends on the context of the problem.